Hello students, in today's lecture we will learn wave optics and this is the theory part 1. The topic which we will cover: Huygens principle, coherent sources, interference of light, condition for constructive interference, condition for destructive interference. Disclaimer: the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So, topic is wave optics. According to Huygens principle, light is a form of energy that travels in the form of wave through a hypothetical medium, and that hypothetical medium known as ether. This medium was supposed to be all pervading, transparent, extremely light, perfectly elastic and ideal fluid. Light waves transmit energy as well as momentum and travel in the free space with a constant speed 3 into 10 raised to the power 8 meter per second. So this is the speed of light in vacuum. However, in a material medium, their speed varies from medium to medium depending on the refractive index of the medium. So speed of light is depending on the refractive index of medium and it varies for different mediums. Next is wavefront. When we drop a small stone on a calm pool of water like this, suppose initially this pool or is calm. So when you drop a small stone at this point, waves spread out from the point of impact. So where the you where the small stone dropped at, so at that point we called point of impact. This point is point of impact, and from this point waves spread out in outward direction. Every point on the surface starts oscillating with time. At any instant, a photograph of the surface would show circular rings on which the disturbance is maximum. So every point on the surface like this point is starts oscillating with time, and after at any instant a photograph of this surface would show circular like this is a circular rings on which this is a circular rings as shown in this figure on which the disturbance is maximum. Clearly all points on such a circle are oscillating in phase because they are at same distance from the source, or we can say they are at the same distance from the point of impact. This is the point of impact, or we can say this is the point, this is the source from the waves are spread out. Such locus of points which oscillate in same phase or in phase is called wavefront, and the speed with which the wavefront moves outwards from the source is called speed of wave, and this is the point of impact, and the wavefront moves outwards in this direction from the source. So this is, suppose this is the source and the waves are spread out, moves, or we can say moves outwards, and the speed is called speed of wave. Next is, if we have a point source point source emitting waves uniformly in all directions. Then the locus of points which have the same amplitude and vibrate in same phase are spheres, and we have what is known as spherical wavefront. So suppose this is a point source when waves spread out from this point source. So in that case, the shape of the wavefront should be spherical, or we can say spherical wavefront. And that spherical wavefront, suppose this is the point source, and this is the point source, and the distance from the all oscillating waves from the point sets are same, from this point to this point and this to this. Clear? So there is a two spherical wavefront. First is diverging spherical wavefront. So suppose this is the point source, and the in diverging spherical wavefront, the wavefront spread out outward direction like this. This wavefront are spread out outward direction. Second is converging spherical wavefront. In converging spherical wavefront, the waves converge like this. So this is not easily you can see. At a large distance from the source, suppose the source is at infinity. In that case, uh, a small portion of the sphere can be considered as a plane, and we have what is known as plane wavefront. So this is the representation of plane wavefront when the source at infinity. So there is a two wavefront. First one is the spherical wavefront, in that when the source is point source, and second is the plane wavefront when the source at a large distance. So this is the plane wavefront. Next is Huygens principle. According to Huygens principle, each point of the wavefront is source of a secondary disturbance. Suppose this is the wavefront. Suppose this is the first wavefront. This one is the first wavefront. This one. This graph shows the first wavefront, and every point, suppose this point, and this point. Every point in on the this wavefront is the source of secondary disturbance. This point is source of secondary disturbance. This point is the source of secondary disturbance. Also, this point is the source of secondary disturbance. And wavelets emanating this secondary disturbance we call wavelets, or we can say small wavefront. So wavelets emanating from these points spread out in all directions. So spread out in all directions like this. So with the speed of the wave, these wavelets emanating from the wavefront are usually referred as the secondary wavelets. So this is the secondary wavelets. And if we draw our common tangent, this is the common tangent, this point, and this point. So this is the common tangent to all these points referred as to secondary wavelets, this one. So we obtain a new position. So this is the new position of a wavefront at a later time. So this is the second one more wavefront. So this is the way how the waves spread out from the point of impact. So this is the example of spherical wavefront, and similarly in uh, linear similarly in linear wavefront. So suppose this is the linear source, and at every point, each point on the wavefront is the secondary disturbance as from the Huygens principle. So this point is is the secondary disturbance. So when you complete this circle, this one, like this one. So this point is the secondary wavefront disturbance. Similarly, this point is also secondary disturbance, and this point is also secondary disturbance. So a common tangent, this one is common tangent to all these points. We obtained a new wavefront at a later time. So this is the spherical wavefront, and this is the linear. Next is coherent sources. Two light sources are said to be coherent if they emit light of exactly same frequency or wavelength, such that the originating phase difference between two waves emitting by them is either zero or remains constant. So suppose there is a two source of light for sodium lamp and denoted by source of light S1 and source of light second denoted by S2. When both the sources are meet at this point, so like this, at this point here, so can both the sources are coherent? No, because they cannot maintain the constant phase difference during the traveling from this point to this point. So there is a condition for the coherent sources. Light sources are said to be coherent if they emit light exactly same frequency. So suppose both are the sodium lamp, so frequency is same, wavelength is same, but the phase different could not constant. So this is the coherent sources. This is the condition for the coherent sources. Next is interference of light. Interference of light is the phenomena of redistribution of light of energy in space when two light waves of same frequency or wavelength emitted by two coherent sources traveling in a given direction superimposed to each other. This phenomena we called interference of light. So in interference of light, two sources, or we can say at a point two waves are superimposed. If A1, suppose A1 and A2 be the amplitudes of two light waves at same frequency and the phi be the phase difference between them. Phi is the phase difference between the both the waves. Then the amplitude of resultant wave is given by this one. So this AR is the represents the amplitude of the resultant wave, which is equal to under root A1 square plus A2 square plus 2A1 A2 cos phi. So this is the resultant wave formula, and this is important for the exams. And in terms of intensity of light, IR is equal to, this is the resultant intensity, is equal to I1 plus I2 plus 2 under root I1 I2 cos phi. So this is resultant amplitude and this is resultant intensity. So from this relation and this relation, this is clear. Intensity is directly proportional to square of the amplitude. So this is the interference of light. Next is condition for constructive interference. So in case of constructive interference, if at some point in space the phase difference between two waves phi equal to 0 degree, phi is the symbol of the phase difference, or we can say phi equal to 2 n pi, or path difference between the two waves delta equal to 0, or we can say delta equal to n lambda, where n is the integer, then resultant amplitude AR is equal to A1 plus A2. This is the resultant amplitude, and resultant intensity IR is equal to I1 plus I2 plus 2 under root I1 I2 is maximum. So this is the resultant intensity and resultant amplitude in case of constructive interference. In constructive interference, this is the formula for amplitude and resultant intensity. Such an interference is called constructive interference. Suppose there are two waves. For this is first wave, this one, and this is second wave. When both waves are superimposed, when both waves are superimposed, we get a new wave, and the amplitude of this wave is much larger as compared to this wave and this wave. So this is the constructive interference. Second is condition for destructive interference. If at some point in space the phase difference between two waves phi equal to 2n minus 1 pi, so this is the phase difference, this one, or the path difference delta is equal to 2n minus 1 lambda by 2, so this is the delta, such then the such points the resultant amplitude AR is equal to A1 minus A2, this one, and resultant intensity is I1 plus I2 minus 2 under root I1 I2 is minimum, leading to destructive interference. So there is a two case. First is constructive interference and second is destructive interference. In the case of constructive interference, resultant amplitude is A1 plus A2 and intensity is I1 plus I2 plus 2 under root I1 I2. And in the case of destructive interference, resultant amplitude is this one and resultant intensity is this. From this diagram, this is clear that suppose there is a two waves, this is the wave first and this is wave second. When both the waves have a different amplitude, the amplitude is this one, and this is crust and this is trough, and this is amplitude is this one, and amplitude is this, and this is crust and this is trough. So when both the waves are superimposed at a point, in that case both are opposite, so the resultant wave is cancellation cancel out. So this is the condition for destructive interference. And main thing, the first is phase difference, that is phi, and path difference delta, and resultant amplitude this one, and intensity is this. Hello students, in today's lecture we will solve some practice question based on wave optics, and this is practice question part 1. The question which we will solve in today's lecture, first to fifth. So topic is wave optics. Question is, the wavefront of a distant source of light is shape of what? So in this question asks about the what will be the shape of wavefront when the source is have a distant, means source, distant source. For the distant source, what will be the shape of the wavefront? Given options: option A is spherical, option B is cylindrical, option C is elliptical, and option D is plane. So which option is correct? Option A, option B, option C, or option D? You have some time to solve this question. After that, we will provide the solution of this question. So the wavefront of a source, distant source of light is of shape. So we have to find the shape of the wavefront when the source is distant source. When the point source or linear source of light is very large distance. Suppose this rays is comes from infinity. In that case, the source of light at very large distance. So in that case, wavefront are plane wavefronts. So wavefronts are plane wavefront. So option D is correct. Next question. In a Young's double slit experiment, two coherent sources are placed 0.90 mm apart. This is the distance between the two coherent sources. And the fringes are observed 1 meter away. If it is produced, the second dark fringes at the distance of 1 mm from the central fringe, means that the second dark fringe at a distance 1 meter from the central fringe. The wavelength of monochromatic light is will be what? So in this question asks about the wavelength of the monochromatic light. So given options, option A is 60 into 10 raised to the power minus 4 centimeter. Option B is 10 into 10 raised to the power minus 4 centimeter. Option C 10 into 10 raised to the power minus 5 centimeter. And option D 6 into 10 raised to the power minus 5 centimeter. So which option is correct? Option A, option B, option C, or option D? You have some time to solve this question. After that, we will provide the solution of this question. So, in a Young's double slit experiment, two coherent sources are placed 0.90 mm apart and the fringes are observed 1 meter away. If it is produced the second dark fringe at a distance 1 mm from the central fringe, the wavefront of monochromatic light is used will be what? So in this question, we have to find the wavelength of the monochromatic light used. So we will use the formula for the position of dark fringes in Young's double slit experiment. The position of nth dark fringe is given by this one. This is the formula for the position of nth dark fringe. X is equal to 2n minus 1 multiplied by lambda d divided by 2d. So we have to find the lambda. So lambda equal to, you here use the simple mathematic calculation. So lambda is equal to 2xd, x multiplied by 2 into d, 2xd divided by 2n minus 1 and multiply by d. So now put the value of all given terms. Here the 2 into x 10 raised to the power minus 9, that is given is 1 meter away and distance is 1 mm. So put all given terms in this formula. 2 into 10 raised to the power minus 3 multiply by 0.9 into 10 raised to the power minus 3. This is the distance between two coherent sources, this one. So divided by 2 multiply by 2 minus 1 and multiply by 1. D is the 1 meter away. So when you solve this question, lambda is equal to 6 into 10 raised to the power minus 5 centimeter. The wavelength of the monochromatic light is used is equal to this one, 6 into 10 raised to the power minus 5 centimeter. So correct option is option D. Next question. In Young's double slit experiment, two slits act as coherent sources of waves of equal amplitude and wavelength lambda. In other experiment with the same arrangement, the two slits are made to act in incoherent sources of waves of same amplitude and wavelength. Here there is a two situation. In first situation the sources are coherent and in second situation the sources are incoherent. If the intensity at the middle point of the screen in the first case is L1 and in the second case is L2, then the ratio L1 divided by L2 is what? So in this question asks about the what will be the intensity ratio. Given options, option A is 4, option B is 2, option C is 1 and option D is 0.5. So which option is correct? Option A, option B, option C or option D? This is AIEEE 2012 question. So you have some time to solve this question. After that we will provide the solution of this question. In Young's double slit experiment, the two slits act as coherent sources of waves of equal amplitude and wavelength. So here given terms is that equal amplitude, that is A, and wavelength lambda. In other experiment with the same arrangement, two slits are made to act in coherent sources. So here the source is coherent source and in second experiment, or we can say in another experiment, the source is incoherent of the waves of same amplitude and wavelength. If the intensity at the middle point of the screen in the first case is L1 and in the second case the intensity is L2, then what will be the ratio? L1 divided by L2. So we know for the coherent source, intensity is directly proportional to the square of the amplitude. So this is the relation between the intensity and amplitude, where this one. I1 is equal to 4 I naught cos square 5 by 2 is equal to 4 I naught. The intensity add up normally, so no interference. This one case for the coherent sources, in that case I1 is equal to 4 I naught, and in the second case when the sources are incoherent, in that there is no interference. So I2 is equal to I naught plus I naught is equal to 2 I naught. So in this question ask about the what will be the ratio. So I1 divided by I2, that is this is the ratio, is equal to 2. So correct option is B, and this is AIEEE 2012 question. Next question. A mixture of light consisting of wavelength 590 nanometer and unknown wavelength illuminates the Young's double slit and gives rise to overlapping interface patterns on the screen. The central maximum of both lights coincide. Further, it is observed that the third bright fringe is known light coincides with the fourth bright fringe of unknown light. From this data, the wavelength of the unknown light is what? So, in this question asks about the what will be the wavelength of the unknown light, and this is AIEEE 2003 question. Given options, option A is 885.0 nanometer, option B is 442.5 nanometer, and option C 776.8 nanometer, and option D 393.4 nanometer. So which option is correct? Option A, option B, option C, or option D? You have some time to solve this question. After that, we will provide the solution of this question. So a mixture of light consisting of wavelength 590 nm and an unknown wavelength. So here in this question tell us that a mixture of light consisting two wavelengths, and the first is the 590 nanometer and second one is unknown wavelength, illuminates the Young's double slit and gives rise to the two overlapping interference patterns on the screen. The central maximum of the both lights coincide. Listen carefully. The central maximum of the both lights coincide. Further, it is observed that the third bright fringe of the known light coincide with fourth bright fringe. Third bright fringe of the known light coincide with fourth bright fringe of the unknown light. From this data, the wavelength of the unknown light is what? So we have to find the wavelength of the unknown light. So here we will use the nth maxima occurs at a distance, this one, for the both cases. For we have 3d lambda k divided by d is equal to 4d lambda mu divided by d. So we will use this formula. Here lambda k is known wavelength and lambda mu is for unknown wavelength. Thus we have to find the wavelength of the unknown light, that is represented by the lambda mu. So lambda mu is equal to 3 lambda k divided by 4. Dd cancel out both capital and small, so remaining term is this one. So put all the given terms which is given in this question After that you will get the correct solution. So 3 divided by 4 multiply by 590, and this is the wavelength which is given in this question. So after calculating this term, you will be get lambda mu is equal to 442.5 nanometer. And this is AIEEE 2003 question. So solution is this one. So correct option is B. Next question. Two coherent point sources S1 and S2 are separated by a small distance d, as shown in this figure. So there is a, this is source S1 and this is the source S2, and both the distance between both the sources is small d, and the distance between the source and the screen is capital D. The fringes obtained on the screen will be, so in this question asks about the fringes on the screen, or we can say shape of the fringe, what will be on the screen. Given options: option A is points, option B is straight lines, option C is semicircle, and option D concentric circles. So which option is correct? Option A, option B, option C, or option D? You have some time to solve this question. After that, we will provide the solution of this question. So, two coherent point sources S1 and S2 are separated by a small distance d. This is source S1 and this is source S2. This is source S1 and this is source S2, and the distance is between both the sources is d, small d, and the distance between source and screen is capital D. So we have to find the fringes obtained on the screen will be what? So suppose when there is a two sources S1 and S2, and the light waves is incident at this point, clear, and second source and the waves meet up at this point. Similarly for second case. So when the light, or we can say waves incident on the screen and meet up at a similar point, so in that case it will be concentric circles, or we can say the fringes obtained on the screen will be concentric circles, as on this figure. This is concentric circles, this one. So correct option is D, and this is JEE Main 2013 question.